Okay, we're going to finish up our hypothesis testing today. And we're going to look at some examples for proportions. And I do have one calculator up here. The other one I left in my other bag. I apologize. And so I'm going to just show you how to do this proportion using a test on your calculator. And then we'll do an example using a t-test. Okay, so first example. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. June samples 100 first-time brides, and 53 reply that they are younger than their grooms. For the hypothesis test, she uses a 1% level of significance. All right, so number one, what leads you to understand that this is a hypothesis test of a proportion and not a mean? Anywhere in this problem, do they tell you the mean of the sample is?
No, the only information they get is that 53 replied yes.
So that is a proportion. They tell you what proportion of the sample replied yes. So this is going to be a hypothesis test of a proportion. All right, let's write our null and our alternate hypothesis. So she first says that she believes that brides are younger than the grooms, but we don't at this point have a hypothesis test that will compare to proportions. So what's the next thing she's going to do? She's going to conduct a hypothesis test to determine if the percentage is the same or different than 50%. So what is my two hypotheses going to be? Either the proportion is the same, so that's going to be my null, or my proportion is not going to be the same. That is going to be my alternative. So this will be, because of the alternative hypothesis being not equal to, this will be a two-tailed test. So if it's less than, it's left. If it's greater than, it's right. If it's not equal to, it is two-tailed. So I could go through and show you. So her sample said that 53% out of 53 out of 100 said that they were younger than their grooms. So we could go through and find the p-value, the probability of getting 0.53, given that the proportion is assumed to be 0.5. So we could do that, but you're probably not going to do that when you do your homework. So let's conduct the p-test. So what we're going to do, we're going to go to our calculator. And in our calculator, we're going to go to our stat menu. Does everybody have a calculator? Does anybody want to borrow one? And we're going to go over to tests. And then we're going to scroll through. So we've used a z-test. We've used the intervals. And down here at A, I have a 1 proportion z-test. And that is what I am going to use. Okay, and then I'm just going to plug in the information that I've been given from the problem. So she found that 53 out of the sample of 100 said that they were younger than their husband. So the number that said they were younger is 53. So X is 53. That was a sample of 100. And what confidence level am I using here? 99%. Oh, I did an interval. I'm so sorry. Well, if you can't make a mistake a day, what can you do? Well, that was a confidence interval if you're interested in that. Five, 1 proportion z-test. If that's the only mistake I make today, I'm going to be doing well. 1 proportion z-test. I apologize. It's number 5. Well, we found the confidence interval if you're interested in that. Okay. So what is my p sub 0? The assumption is that 50% are less than, or 50% are younger than their husbands or whatever. So her null hypothesis was that p is 0.5. So that's what p sub 0 is. That's 0.5. And then we have the 53 out of 100. At least I got that in there correctly. And this is a two-tailed test. So we're going to choose not equal to. And now we're going to calculate. See if I did this correctly. Okay. So the p-value that we get is 0.5485061291. So what conclusion do we draw from that p-value? And that is the p-value in both tails. So in total, in both tails, you get 0.5485. So in the two tails would be half of that. But what we can see by this number is that's large. That's a large p-value. And my alpha was 0.1%. So if the p-value is greater than my value for alpha, then I'm not going to reject my null hypothesis. So if the p is high, the null is must fly. So what this says is that my sample data is not sufficient to reject the hypothesis that the proportion is 50%. There's not enough evidence to support the claim that it's not 50%. So my p-value, and this is a slide that has an error in it. Let me fix that. So the p-value that we found using the 1 proportion z-test was 0.54. Half of that is in each tail. So half of the p-value is 0.274. Since alpha is less than the p-value, or the p-value is greater than alpha, we cannot reject the null hypothesis. So our conclusion is at a 1% level of significance, the sample data do not show sufficient evidence that the percentage of first-time brides who are younger than their husbands is different than 50%. Your data did not support the conclusion that it isn't 50%. All right, let's do another proportion. And how do I know this is a proportion? Because it's in percentage. That is correct. Suppose a consumer group suspects that the proportion of households that have 3 cell phones is 30%. A cell phone company has a reason to believe that the proportion is not 30%. Before they start a big advertising campaign, they conduct a hypothesis test. Their marketing people survey 150 households, and the result that 43 of the households have 3 cell phones. So what's my null hypothesis? What's my alternative hypothesis? So what's your null hypothesis? What are they saying?
30%.
That is 30% or not. So it would be the proportion is 0.3 or the proportion is not 0.3. So this is a two-tailed test. And that is important when you're conducting a two-tailed test so that you'll know, is it greater than, is it less than, or is it not equal to? So which one is it going to be? Well, it's going to be not equal to, because that's what it says, not equal to. Okay, so what do we know? Well, we know that they conducted a survey, 43 out of 150 said that they have 3 cell phones. So we have everything we need to go find the p-value. So I'm going to go back and I'm going to go to stat, tests, 1 proportion z-test. We're looking at a null hypothesis. Is my proportion 30%? In my survey that was conducted, I found, did I write it down? How many out of how many? It was the sample size was 150, right? So what was the number that said that they had 3 cell phones? 43, thank you. Somehow that didn't get written down in my notes. I don't know how, but it didn't. It's a two-tailed test, so it's not equal to. Calculate. So what's our p-value? Huge, 0.72. That's pretty big, really big. So what's that tell us? What's that really big p-value tell you? What you gonna do? What's that tell you? What's the alpha? And if they don't tell me what alpha is, if they don't tell me, I assume it's 0.05. If alpha is not given, make an assumption it's 0.05. So what's that point? I don't care what alpha is. What's that 0.72 tell you? That's huge. So can you reject the null hypothesis? No, you cannot reject the null hypothesis. That p-value is so big, there is not evidence to show that it's not 30%. So based on the sample that you've taken, there's not sufficient evidence to say that the proportion is not 30%. So you do not reject the null hypothesis because there's not sufficient evidence to conclude that the proportion of households that have 3 cell phones is not 30%. Your sample evidence didn't support that at all. Alrighty. The next hypothesis test we're going to conduct, we're going to put data in our calculator, which is probably typically the way you're going to go. The National Institute of Standards and Technology provides exact data on conductivity properties of materials. Following are conductivity measurements for 11 randomly selected pieces of a particular type of glass. And there are your 11 data points. Is there convincing evidence that the average, now what kind of hypothesis test am I going to conduct? Well, not a proportion, but a hypothesis test on a mean, because they got an average. Is there convincing evidence that the average conductivity of this type of glass is greater than 1? Use a significance level of 0.05. Assume the population is normal. Okay, what is missing from this data? Standard deviation. So since standard deviation is missing, you're going to conduct a T hypothesis test, okay? Because there is no standard deviation. So what's my null and alternative hypothesis? What are we trying to show here? Is there convincing evidence that the average conductivity of this type of glass is greater than 1? So that would be that mu is greater than 1. So this would mean that this is a right-tailed test. So what would be our null hypothesis? Mu is less than or equal to 1? Okay, so what I would do is I would put these 11 pieces of data in a list. So now I can conduct the hypothesis test using that the statistics calculated from that list. So have you done that? If you want to do that, have you done that? So I'm going to go to my stats in my list. And I put this in L3 because the other day we had a bunch of data going in. So here is these 11 pieces of data in my L3 list. Okay, so now I'm going to conduct the hypothesis test using that data. So I'm going to get out of there and I'm going to go to stat, tests, and I'm going to find my z-test, my t-test. Okay, and I'm going to conduct my t-test using my data. I'm not going to type my stats in. I'm going to use the data that I input. So make sure that's highlighted. Okay, and what are we testing? We're testing to see if the data support that the mean is greater than 1. So I'm going to put 1 in for mu sub 0. The list that I'm using is L3, so I need to make sure that I tell my calculator the correct list to calculate the statistics from. I don't have a frequency list, so that's just going to be 1. And this is a right-tailed test, right? We're trying to determine if it's greater than 1. So I'm going to highlight greater than. And then I'm going to go back down here and calculate it. Does that look correct to you? Is that what yours looks like? I'm using my data from whatever list I put in, that data in. I'm testing if mu is greater than 1, so mu sub 0 has to be 1. Personally, I'm using L3 because that's where I put my data. I don't have a frequency list, so that's just going to be 1 because each data only occurs one time. It's a right-tailed test because my alternative hypothesis is testing if mu is greater than 1. So we're going to calculate. What do we get? We get a p-value of 0.03586. And you'll notice that it also calculates the mean of standard deviation of my sample. So if you need to know the mean, there it is. If you need to know the standard deviation, there it is. It also calculates the t-score. So again, if this is a normally shaped curve, this is the probability, the area under the curve to the right of that t-value, to the right of 2.0137. Okay, so my p-value is 0.0356. And I want that p-value because that's what I'm going to compare to my alpha. So we got p and now we're going to compare that to alpha. And we're using a significance level of 0.05. 0.036 is smaller than 0.05. So my p-value is less than alpha. What's that mean? Reject. If the p is low, the null must go. So we're going to reject the null hypothesis. So our sample data does support the conclusion that the mean conductivity is greater than 1. So since we rejected the null hypothesis, we say that our data supports the alternative hypothesis. If you don't reject, then you say your data doesn't support the alternative. If you reject, you say your data does support the alternative. And in your notes, in the PowerPoint slides, here is the step-by-step on your calculator how to do this. And the one thing we haven't done yet, which we probably should, is to draw this so you can see what this looks like. Since the p-value, p equals 0.036, is less than our alpha value, we reject the null hypothesis. It's reasonable to state that the data supports the claim that the average conductivity level is greater than 1. Okay, let's go back over there and let's do that drawing. So if I go back to my stat menu and I go to my t-test, number 2, and instead of calculating, let's go down here and draw. Now, what I should have done is make sure I don't have anything in my y equals or my stat plots on, because if I do, it's going to spasm. Let's do, let me quick check. There it goes. There it goes. So what this draws for me is exactly what it's doing. So it calculated, this is a t-test, so it calculated t for me, which is 2.0138. And the p-value is the area under the curve to the right of that t-value, that t-score. So the p-value is the probability that I get a value as extreme as the one I got from my sample. So the probability is pretty small. It's less than alpha. So if the p is low, I reject the null hypothesis. That probability, or that mean is less than or equal to 1. And I said I should have made sure I didn't have anything in my y equals, which I did, which was okay. It didn't graph it. Normally, you want to make sure y equal is clear and that your stat plots are all off. Okay, what kind of test are we going to be conducting here? Can you tell by just looking? Is it on a mean or is it on a proportion? proportion. And why did you conclude that?
The mean is majority, so we're given the sample and combination of the.
Yeah, they don't tell you the mean anywhere, but they do tell you the proportion of people out of the sample have this issue. So in a study of 420,019 cell phone users, 172 of the subjects developed brain cancer. Test the claim that cell phone users develop brain cancer at a greater rate than that for non-cell phone users. The rate of brain cancer for a non-cell phone user is 0.0340%. Since this is a critical issue, use a 0.005 significance level. Explain why the significance level should be so low in terms of a type 1 error. Well, a type 1 error, if you reject the null when it's true, then you're going to reject that this is at a higher rate. And you're going to assume it isn't, and that could be a problem. Okay, so what's our null and our alternative hypothesis? Well, 0.034% of the population of non-cell phone users have brain cancer. So our null hypothesis would be, well, we're trying to show that this is a greater rate than that for the non-cell phone users. So we're trying to show that the proportion is greater than 0.00034. 0.034% is 0.00034. Okay, so if that's our alternative hypothesis, our null hypothesis would be what? Less than or equal to? Okay, so I am going to conduct a one proportion z-test using this information. P sub 0 is going to be 0.00034. Our sample, there was 172 out of a sample size of 420,019 that had brain cancer. So I'm going to plug all that in and see what happens. Go to my stat menu, tests. We're going to conduct a one proportion z-test, number 5. My proportion in my null and alternative hypothesis was 0.00034. In my sample, I had 172 out of a sample size of what? 420,000. Since my alternative hypothesis was greater than, it is a right-tailed test, which I already have highlighted, and we're going to calculate. Okay, what's my p-value? My p-value is 0.007. Okay, now we're going to compare that p-value to alpha. 0.007 is greater than our predetermined value for alpha. So our p-value is greater than our alpha. So what do? You can't reject the null hypothesis. If the p is higher than alpha, if the p is high, the null must fly. So if P is higher than alpha, you fail to reject the null hypothesis. So what's this say? Well, what this says is that the sample doesn't support the conclusion that the proportion is higher than the average, or the proportion, excuse me, not average, the proportion of non-cell phone users. So that's a good thing. The sample doesn't support that the proportion of cell phone users have a higher rate of brain cancer than non-cell phone users. Good thing. Since the p-value is 0.0073 is greater than our alpha, 0.005, we cannot reject the null hypothesis. Therefore, we conclude, we truly do conclude, that my computer is having a spasm. All right, see if I can do it now. Therefore, we conclude that there's not sufficient evidence to support the claim of higher brain cancer rates for cell phone users. If we commit a type 1 error, we are essentially accepting a false claim. Since the claim describes cancer-causing environments, we want to minimize the chances of incorrectly identifying causes of cancer, which you can't even see. It needs more coffee. Okay. According to the US Census, there are approximately 268,608,618 residents age 12 and older. Statistics from the Rape, Abuse, and Incest National Network indicate that on average, 207,754 rapes occur each year, male and female, for persons aged 12 and older. Well, that's a sobering statistic, isn't it? This translates into a percentage of sexual assaults of 0.078%. In Daviess County, Kentucky, there were reported 11 rapes for a population of 37,937. Conduct an appropriate hypothesis test to determine if there is a statistically significant difference between the local sexual assault percentage and the national sexual assault percentage. Use a significance level of 0.01. Are we concerned about Daviess County, Kentucky? Okay, so what kind of test are you going to perform? Proportion or mean? Why are you performing a proportion? Because nowhere in here do they give you a mean. Okay, so what's my null and alternative hypothesis? Conduct an appropriate hypothesis test to determine if there is a statistically significant difference. So is the proportion in Daviess County, Kentucky, the same as the proportion nationally, or is it different? So I might have conducted a test that says, is it greater? Because I might be concerned if it's larger than the national average. Okay, so this is a two-tailed test. Alpha is 0.01. So what are we going to do? P sub 0 is 0.00078. What do we have? 11 out of what, 37,937? So I'm going to conduct again a one proportion z-test number 5. My p sub 0 was what? 0.00078. That is the percentage on the national level. In this county in Kentucky, there were 11 out of 37,937 people over the age of 12. It's going to be a two-tailed test, a not equal to, because that's the way this problem was stated. I might look at it differently if it were me. And we calculate. So the p-value we get is 0.0006. It is given to me in scientific notation because it's such a small number. So we see over here, the e to the -4 indicates that it is a scientific notation. So I will have 3 zeros before this 6. So 0.006288. So let's go back to our slide. So the p-value we calculated was 0.00063. The alpha that we used was 0.01. The p-value is less than alpha. So if the p is low, the null must go. So we're going to reject the null hypothesis. So we're going to say that there is sufficient evidence to say that the proportion of sexual assaults in this county is different than the national average. You might go back and look at the p-hat. What is the proportion based on this data? What was the p-hat? It was 0.0002, which is actually less than the national average, which was what, 0.0009 or 8, excuse me. So you might conclude that it's less than the national average, and you might test to look at that. You know, to conduct a hypothesis test saying that the proportion in this county is less than the national average. But we are rejecting the null hypothesis. Since the p-value, p is 0.00063, is less than the alpha, the sample data indicates that we should reject the null hypothesis. In conclusion, the sample data support the claim that the proportion of sexual assaults in Daviess County, Kentucky is different than the national average proportion. And that is the end of chapter 9. Are there any questions? If you do, you know how to reach me, right? By email, send a message through my Open Math, whatever works best for you. All right, if there aren't any questions, I will see you on Tuesday. Have a great rest of your week.